Hey, welcome everyone. Have you ever stopped and wondered what's actually happening inside the tech you use every single day? You know, your USB drives, your camera, your phone? Well, today we're going to peel back the layers of one tiny little memory chip and decode the secret blueprint that makes it all work. Just think about it for a second. All your photos, all your files, all your music, we just call it data. But what does it actually look like on the inside? I can tell you it's not a tiny little picture or a microscopic document. It's something way, way simpler. And our guide for this adventure is this document right here, a technical data sheet. Now, I like to think of it as a secret blueprint. It's basically the instruction manual written by the engineers who designed the chip, and it holds all the keys to its secrets. So let's start decoding. All right, first up, the secret blueprint. And, like with any good blueprint, the very first thing we have to do is figure out what we're even looking at. It all starts with this string of letters and numbers. I mean, it just looks like some kind of cryptic code, right? But believe it or not, this is not random at all. This is the chip's official part number, and every single one of those characters has a very specific meaning. And here's our decoder ring. PN, that's the vendor, XTX. 27G tells us it's a 3.3-volt NAND flash chip, which is just a common type of memory that doesn't need power to hold on to data. 01A reveals its capacity, 1 gigabit. It even tells us the package type, that it can handle some pretty extreme industrial temperatures, and that it's an eco-friendly green package. Isn't that amazing? It's like a whole biography in just one line of text. Okay, so we know its name, but what does this thing actually look like? Well, this diagram shows us the underside. You see all those little circles? Those are actually tiny solder balls. They're the physical connections, the little gateways that let electricity and all our data flow in and out. So, section 2, decoding the exterior. We figured out the name and we found the front door, so to speak. Now, let's follow those connections and step inside. And this is where those gateways lead. This is the internal block diagram. It's basically the chip's entire nervous system. It shows how all the different parts, like the logic control and the memory array itself, are all wired together. We are officially inside the blueprint. Section 3, inside the memory library. Now, at the very heart of this chip is something called the memory array. And honestly, the best way to understand it is to stop thinking about circuits and start thinking of it like a huge, incredibly organized digital library. And of course, every good library needs a floor plan. This diagram right here shows us exactly how that 1 gigabit of data is structured. Now, it might look a little complicated, but the rules are actually super simple and really logical once you see them. Okay, so the smallest piece of our library is called a page. Just think of it like a single page in a book. For this chip, every page holds exactly 2,176 bytes of data. And here's the most important rule. You can't just write one word on the page. You have to write a whole page all at once. Now let's zoom out a bit. A group of 64 of those pages forms what's called a block. So if a page is a page in a book, then you can think of a block as a whole bookshelf in our library. This is really important because of another rule. While you can write one page at a time, you can only erase an entire bookshelf at once. You can't just go in and remove a single page. So how big is this entire digital library? Well, it's made up of 1,024 of these blocks. That's right, 1,024 bookshelves, and each one of those holds 64 pages of your data. This is the super organized system that's storing all your files. Next up, section 4, speaking its language. Okay, so we've got this incredible library, but how do we actually tell the librarian, the chip's internal control circuit, what we want it to do? Well, we have to speak its language. And this is its vocabulary. To get the chip to do anything, we send it commands as these little hexadecimal codes, which is really just a number system computers like to use. And as you can see, there's a specific code for erasing a block, another for programming, which is just a fancy word for writing, to a page, one for reading from a page, and even one to just ask, hey, are you busy right now? It's a really precise, simple language. Let's just take an example like erasing one of our bookshelves or blocks. It's a simple 3-step conversation. First, you send the setup command, which is 60 hex. Then you tell it the address of the specific block you want to erase. And finally, you send the actual erase command, D0 hex. And that's it. The chip just takes over and handles the rest. So how fast does all this happen? Well, writing data to just one of those pages, filling up one page in our library, takes on average just 300 microseconds. That's 300 millionths of a second. That incredible speed is exactly why when you hit save on a small file, it feels totally instantaneous. It's all because of this tiny number. Okay, Section 5, Powering Your World. We have gone deep into the guts of this blueprint. We've talked about pages and blocks and commands. But now let's zoom all the way back out. Why does any of this even matter? What makes this little chip so important? Well, one of the biggest reasons is this number, 10. This chip is designed to hold on to your data for 10 years, even with zero power. That's why you can pull some old USB drive out of a drawer a decade later, and bam, your photos are still there, perfectly preserved inside its little digital library. So when you put all of that together, the speed, the organization, and that incredible data retention, it makes this chip absolutely perfect for things like USB drives, voice recorders, and digital cameras. The blueprint itself calls it ideal for high-density non-volatile storage, which, in plain English, just means a way to store a whole lot of data that sticks around even when you turn the power off. So there you have it. In just a few minutes, we've gone all the way from a cryptic line of code to a fully fleshed-out digital library. We've translated the language of engineers into bookshelves and pages, and we've decoded the secret blueprint that makes so much of our digital world even possible. And that kind of leaves me with one final thought for you. We just peeked inside one tiny component. It really makes you wonder, what other secret blueprints, what other digital libraries are hiding in plain sight inside the technology that you use every single day?